Owning or building your own home is a big part of the American dream, but if you build on permafrost, that dream can slowly become a nightmare. This video will help you understand the phenomenon known as permafrost. We will rely on the information provided by Dr. Terry McFadden, co-founder of the Permafrost Technology Foundation and a professor of Arctic Engineering at the University of Alaska Fairbanks, and Dr. Tom Kinney, vice president of the Permafrost Technology Foundation, a faculty member of the University of Alaska Fairbanks, and a vice president of Shannon & Wilson, a geotechnical consulting firm. In the next 30 minutes, we will answer 5 questions. What is permafrost and how does construction affect it? What happens when permafrost thaws? What are appropriate foundation types? How do you tell if you have a problem? And what to do if you do have a problem? Permafrost is permanently frozen ground. It occurs over 4/5 of Alaska. If you take a string of temperature measuring devices and stick them in the ground so that you can measure the temperatures at several depths, there will be a minimum and maximum temperature at each depth. Dr. McFadden explains.
If we take a thermistor string and put it in the ground so that we can measure temperatures from the surface down to various depths, and we measure the temperatures all year long, we find that on the average, sometime in January usually, we'll find a minimum annual surface temperature, and sometime in July we'll find our maximum temperature. And of course, the mean temperature is the average between those two. If we do the same thing at the various depths, we find in each case, at each depth, there is a minimum temperature and a maximum temperature, but the minimum temperature isn't as cold as it was at the surface. And incidentally, it comes just a little bit later in the season. And the maximum temperature is just a little bit cooler than the surface. If we then draw a line through these dots, we have an envelope or a boundary of minimum temperatures and a boundary of maximum temperatures, the red line. And the yellow line represents the mean annual temperature between those two. All temperatures in the soil at every depth have to be between those two lines because that's what we measured. And we found that it never got warmer than this nor colder than that at each depth. If we put the 32 degree or 0 degree C line on here, that temperature line represented here, and we see that it passes through the maximum temperature here and once again here. This means that temperatures of the soil below this point never get up to freezing. And once again, at this point, temperatures again go above freezing. The area between there, here to here, is always below freezing, and that's the area we call permafrost. We have an active layer here that freezes and thaws every year, and then a permafrost layer here that never thaws throughout the year. When we change the site by construction or clearing or anything that changes the thermal input into the site, we're going to change the position of that maximum temperature curve because now more energy is getting into the soil, and we may get a new temperature curve that looks like this line. And we see that the problem is that the temperature at which it crosses the 32 degree line, or the position at which it crosses the 32 degree line, moves down. We've lost that much permafrost. And down on the bottom, it moves up. The result, of course, looks like this. After the construction, we have a new permafrost thickness. We've lost permafrost top and bottom. All of the ice that was in this layer turns to water and leaves voids which the surface can then collapse into.
To see what happens when permafrost thaws, let's take this beaker filled with ice-rich or non-thaw stable gravel. Notice what happens as we turn on the heat lamp to thaw the beaker. Through the magic of time-lapse photography, we can see that the ice-rich silt has turned to mud and would no longer prove to be a stable surface to build on. From a foundation standpoint, we are concerned about construction on the ice-rich soils. They may settle during thawing or much later as voids and loose soils collapse. Ice-poor permafrost may be a serious problem in developing wells and septic systems. The classical progression goes like this. The house is built in the summer and sold before the house is heated significantly above air temperature. As time progresses, heat from the house progressively pushes the thaw bulb downward. When ice-rich permafrost or ice thaws, the building settles. It may take several years for the thaw bulb to get to non-thaw stable soils, and it may be several years after that before the settlement has reached alarming proportions, and everyone involved finds out how much trouble they're really in. One example of this scenario over permafrost terrain is this radio station on Farmers Loop Road. There are several basic types of foundations that can be used on permafrost terrain. The choice as to which one to choose will be based upon design requirements, the soil and weather conditions at the site, and economics. The most obvious is to excavate the non-thaw stable material and replace it with thaw stable material. This is a very common technique in areas where the depth of unsuitable material is less than about 20 feet, and there is ample low-cost suitable material around. Another solution would be to thaw the unsuitable material and consolidate it. Another technique is to keep the permafrost frozen forever. In some climates, it's possible to let the outside air flow under the building to keep the permafrost frozen. In other areas, it's necessary to add cooling systems to keep the ground frozen. Another solution is to support the building on piles. The piles may either go through the ice-rich permafrost or be founded in the ice-rich permafrost with provisions for keeping the permafrost from thawing. Yet another foundation type is a rigid slab, made so stiff that it will bridge voids developed beneath. There is the potential, however, for the entire building to tip, hence it cannot be used where this would be critical. The final solution is to construct the foundation with an internal jacking system so that the building can be maintained level while the foundation settles. Excavation and replacement is used in areas where the depth of unsuitable material is reasonable, the groundwater problems will not be prohibitive, and there is an economical source of acceptable material. It is common to over-excavate 20 feet and haul material 20 miles to a site. Farmers Loop Road near the University of Alaska recently included a 25-foot excavation and a 30-foot backfill. Thawing and pre-settling is used in soils which will consolidate to a suitable competency. Manual pre-thawing is usually more expensive than excavation and replacement for shallow materials and is usually more expensive than other solutions for an entire foundation. The airport post office building was pre-thawed using steam points and pre-settled with a 15-foot high pile of dirt left in place for 30 days. It is possible to pre-thaw naturally if time permits. Clearing the ground surface will increase the average summer temperature, and in areas of very warm permafrost, this may be enough to thaw up to 20 feet of permafrost in 20 years. This area off of Farmers Loop Road in Fairbanks was cleared in the mid-1950s. By 1975, it had thawed to a depth of 20 feet, and by 1990, thawing had progressed to 30 feet. This process can be speeded up by covering the surface with insulation in the winter to keep it from freezing. There are several methods of keeping the permafrost frozen. The least sophisticated is to elevate the structure and allow outside air to blow under the structure and keep the ground frozen. General design guidelines include keeping the crawl space clear, as is shown here, providing shade, and protecting the utilities. The next level of sophistication is to force air through a crawl space or a series of ducts. The air may be forced by fans. The structure has either an open crawl space or a series of ducts. Fans are then designed to give the proper airflow. The fans are set to run anytime the outside air temperature is lower than the crawl space or ducts. If the forced convection will not provide enough cooling, then we can install a refrigeration system under the structure. We can use active refrigeration, which basically consists of a large freezer which pumps cold fluid through a series of cooling ducts which are placed under insulation under the structure. The Kotzebue Senior Citizens Cultural Center, shown here, has 3/4-inch diameter copper cooling coils on 18-inch centers under 4 inches of insulation. The cooling is provided by chillers in the summer and by radiators during the winter. Passive refrigeration can also be used, as shown here on the FAA Flight Service building in Fairbanks. The pipes are thermoprobes consisting of 3-inch pipe with one end buried in the ground under the structure and fins on the other end. The pipe is filled with CO2, leaving the bottom portion liquid and the top portion gas. When the fin gets cold, it causes the gas to condense on the inside of the pipe. This reduces the vapor pressure and causes the liquid to boil. The boiling cools the liquid, which in turn cools the ground. The system pumps heat out of the ground when the temperature of the air is lower than the temperature of the pipe in the ground. The design criteria is to keep the summer thawing less than the winter freezing. Piles can be used to support the structure in ice-rich permafrost. The piles under this structure were placed in ice-rich permafrost, but the ground is thawing and the piles are settling. This structure on the Krell test site is built on a very stiff foundation. Notice where the ground has settled away from the foundation without causing damage to the building. This last method is to accept the fact that the ground surface is going to settle and to place the foundation on a set of jacks that can be used to re-level the structure whenever the settlement gets out of tolerance. This house near Farmers Loop in Fairbanks was about 15 inches out of level. It is being re-leveled and the foundation is being replaced by the jacking system. This method is gaining acceptance for an economical foundation over ice-rich permafrost. Caution should always be used when heated and unheated portions of a building are attached, and if a foundation is designed to be heated, it should never be allowed to freeze. Outside window wells and stairwells frequently cause trouble by frost heaving vertically and laterally. Frequently, decks and stairs settle or heave differentially from the rest of the structure. There are 3 basic steps to evaluating a piece of property. Do a visual inspection, collect the history on the site, and perform a subsurface investigation. Let's start with the inside portion of the visual inspection. First, we look closely for cracks, particularly around doors and windows or in corners. It is normal for houses to have cracks caused by drying and/or temperature changes. These cracks are normally around sheetrock joints and are fairly small. Be particularly wary of cracks that cut through sheetrock or that show more than 1/16 inch of movement. Look at the level of the floor and the countertops. A carpenter level works very well for determining the level. Use a carpenter's square to check the corners of rooms and the door jambs and window sills. In the absence of a store-bought square, you could use the back of a pad of paper or any other square object. Often the doors and windows won't open and close or have gaps around them. Pay close attention to recent painting or patching and look for places where the molding may have been reset or a door rehung. Many of the same things can be seen from the outside if you look carefully. Look for the level and straightness of the eaves and the ridgeline and siding. This may require backing up or climbing up a bank to get a better vantage point. Look at the vegetation. Black spruce and/or thick ground vegetation are frequently indicators of shallow permafrost, but be wary of the old adage that birch trees indicate an absence of permafrost. Take a close look at the birch trees around this house on Farmers Loop Road in Fairbanks. Take a good look at the terrain. Dips, gullies, and holes are caused by drainage, man, or thawing permafrost. If you see these features and they cannot be explained by drainage or landscaping, then they are probably thermokarst. Thermokarst can be shallow depressions or swales or deep open holes. Sometimes the vegetation will be tilted in areas where the ground has settled unevenly. Look at the surrounding terrain. If the site is in a low area, it will probably be colder than the surrounding areas, and drainage may be a problem. The north side of the hill and heavily vegetated areas are generally relatively cool. Now let's look at the foundations. Be prepared to get dirty if you expect to get any meaningful information from this part of the investigation. If the building has a crawl space like this one on Belane, get in it. Whether it does or does not, take a good look around the outside, including behind the hedges, stairwells, and wood piles. Look for cracks in the concrete and block walls. Look for signs of re-leveling. Check for shims, bracing, and signs of new construction. Put a level on the footing and stem walls and look for signs of shifting or settling. Take a good look around the septic system if there is one. Septic tanks and drain fields are generally warmer than the surrounding terrain and may cause settlement of ice-rich permafrost. Since there can be no vertical drainage through permafrost, it is likely that the septic system will be mounded or will have experienced failures. If the structure has a holding tank, it may be an indication that the structure is on ice-rich permafrost. Next, we want to find out as much as possible about the site history. We can look at engineering reports, borough reports such as building permits and tax history, well records, and finally, talk to neighbors. All of this information can be used to help evaluate the condition of the site. If the structure is badly damaged, one can assume that the conditions are not very good. Otherwise, all we have is circumstantial evidence. It is necessary to do a subsurface investigation to tell for sure if there is a permafrost problem, and if so, what the impact on your structure will be. Borings are the most direct method of determining if permafrost is present, and if so, its engineering properties. Typically, one hole about 40 feet deep is drilled and sampled for the initial investigation. Either split spoon or core samples are usually taken nearly continuously throughout the depth of the boring. If this information and the information gathered above indicate a lack of permafrost, the investigation is usually completed. If any of this information indicates the existence of permafrost, more explorations might be called for. Geophysical methods, including electromagnetic surveys, ground-penetrating radar, and seismic refraction analysis, may be used to evaluate the subsurface conditions. Once all of the information has been gathered and considered, you should have a very good understanding of the site conditions. Even after all this work, there is still no guarantee that there isn't any permafrost under any portion of the building, even if none was found. The boundary between permafrost and no permafrost can be near vertical. So now, what do you do if you determine that the structure has a problem? If your house is on non-thaw stable permafrost and it was not designed and constructed for this, you have a serious problem. If the structure has undergone stress, it will be necessary to re-level it. Once this has been done, there are three basic options. Stabilize the site, move the structure to a more suitable site or foundation, or finally underpin the structure in such a way that it can be easily re-leveled in the future. Some structures are relatively easy to re-level and others are very difficult, if not impossible to re-level. Structures with post and pad foundations or pile foundations are relatively easy. The building is jacked up and the foundation is extended to meet it. Care must be taken to replace the shear and movement carrying capabilities of the foundation so that the next wind or earthquake does not knock the foundation off of its foundation. Structures with crawl spaces are more difficult to re-level, but still, it's usually practical. Sometimes it's practical to jack the house up off the foundation and place shims between the floor and the foundation. Sometimes it's better to put the jacks under the foundation and lift everything and fill in under the footings. Reconstructing the walls to the crawl space can sometimes be very costly. If the structure is a slab on grade, it's probably not worth re-leveling. Grout jacking has been done, but it's very costly and it's not always very successful. Re-leveling the house from the top of the foundation and constructing a new floor may be an option, but it's always very expensive. If the foundation is very stiff, it may be possible to lift the entire structure from the outside perimeter. This is not possible very often and generally will not result in a very level final project. Once the structure has been re-leveled, it must be founded on one of the previously outlined acceptable foundation schemes. The trick is to find the most economical system that can be installed after the structure has been built. Under the right conditions, the foundation modification can be as easy as opening up the crawl space to allow free flow of air, and planting vegetation or installing a deck to keep the perimeter of the structure shaded in the summer and snow-free in the winter. If the air is cold enough but the airflow is not enough, it may be necessary to add a fan to blow the air through the crawl space. If this is not enough, you may have to add thermoprobes or a mechanical refrigeration system. Moving the structure may be a viable option under some circumstances. This structure was moved about 100 feet, but unfortunately, the new foundation was no more suited for the conditions than the old one, and the building started to settle again. Forced convection has stabilized it at present. It is possible to lift some structures and place them on 2 or 3 beams, which run completely under the structure, and then support the beams on stabilized foundations placed outside of the structure. There are relatively few structures that lend themselves to this approach very well, and the technique is generally expensive. It may be best to install jacks under the structure and plan on re-leveling again in the future. This can be as simple as leaving the jack pits open for easy access. The next level of complexity is the system where each jack can be accessed without going under the structure. There are currently designed foundation systems that are controlled from one location and others that are computer controlled to keep them level without human intervention. In summary, there are 3 things that you must do if you are to be involved in the construction industry in areas where there may be permafrost. The first is to learn about permafrost so that you know what to expect. Second, you need to establish if you have a permafrost problem or not. And third, you have to make sure that any foundation on permafrost is suitable for the conditions. The university and some libraries have books on the topic. There are several films on northern construction that are well worth viewing. The university has several. The public library may be a source, and the U.S. Army Cold Regions Research and Engineering Laboratory in Hanover, New Hampshire are good places to start. There are seminars given at various times around the state. They are usually interesting and free. Watch for them in your area. How do you determine that you have a problem? First, do a thorough site inspection from top to bottom and from inside and out. Then get as much information as is available about the site. Lastly, do a permafrost investigation. If you determine that you do have a problem, get professional help. It will be well worth the expense in the long run. Remember that it's always best to do it now. The longer you wait, the worse the problem will become, and the more expensive it will be to fix.